Okay, hopefully you can hear me. I got your email. We'll go over some concepts. So first, just to go over, these are the alkene reactions that we've seen so far. I'm just gonna draw a little line here. These are the new ones that we see this week. And these are all our radical reactions. And so, and let me just grab my old notes from when I took this class. But I wrote a good little summary of the reactions that I just wanted to share with you. And I'm hoping that it is of use to you. Geez, how long is this chapter? Okay, here we go. Okay. So on these reactions, some things to think about as you are seeing them is that anything that's some sort of hydrobromic, hydrochloric, oops, iodic, right? These are all going to be the same. They're all going to kind of look the same here. And they are, we've got these two carbons that we're looking to try to make a bond with at some point, right? And so we're going to see that this is going to be your Markov-Nikov. All right. No promises on the spelling, but hopefully you get the point. Um, and some things just to point out here is that there is a cation intermediate in these first two. And so what that means is that rearrangements are possible. Okay. That doesn't necessarily mean that they will be arrangements, but for the sake of this class, if the cation can be on a more stable carbon, which means a more substituted carbon, if you can have a more stable cation, which means that it's on a more substituted carbon, then it will have a rearrangement. So those are just two things to note with that one. Anywho, with this next one here, we also have, again, I'm going to just do least substituted carbon in green and more substituted carbon in red. Same thing here. So the difference here is that this one actually does show a methyl shift. And so there is our original carbons, but what we actually see is that we end up with this hydration reaction over here. And so that has entirely to do with mechanism. But this will also be a Markov-Nikov. I'm not going to spell it all out, but Markov-Nikov, right? And so we don't necessarily see a shift on this one here because that is the most stable spot for cation to be on. But on this molecule here, we can see that if we are to put a cation right here, it's not the most stable. It is only a second degree cation, where this could potentially be a third degree cation. So what we see is this methyl shift that moves over here. And that is demonstrated here. Here's that methyl. And here's that carbon that was initially in the carbon-carbon double bond. And so we see that our cation would then move here, which is where the OH would attack. It would actually attack as an OH, right? And then, but that's why we see this OH move here, right? So in general, I would say for your heuristics is to know that when you're looking at this, a lot of it, you're going to want to get really familiar with what each of these reactants are doing to your reagents and your products. Um, so yeah, so anytime you see this, you are going to have, you're going to look out for a cation. Anytime you see any of these acids, um, like I said, chloric, bromic, iodic, you will also most likely see a cation that will need to be rearranged. Then we get down to Br2. Um, Br2 will be anti-addition. Um, and so we will see in here that we have this backside attack where we'll have a bromine or whatever, right? But our bromine are on opposite. One is on a wedge and one is on a dash. Okay, so that's anytime we see this here, Br2, and then CCl4 is just an inert solvent, so it's not necessarily a part of the reaction, it's just there to help um, stabilize or move things along. So then when we see Br2 with ETOH, so really what ETOH looks like is, imagine it's somewhat like an ET is just means ethyl, right? But imagine it's kind of like a water molecule. And, if I wanted to draw it out, I could just do this, right? 1 and 2 makes that an ethyl, right? This is a C2, and this is a C3, right? These are like little hydrogens. But anyway, it's just a bigger R carbon chain, hydrocarbon chain. So that's what that looks like. So first what we're going to do is we're going to have very similar, and this is also going to be anti-addition as well as hydration. So we're adding an alcohol. So let me see. So this is also anti-addition. This really has a lot to do with the fact that um, bromine is big and it is kind of holding this place. And I'll show you a mechanism, but it's kind of holding a place here, and it's holding this space here. And so imagine that this is planar, right? And then on top of like the page, so to speak, bromine is holding this space, and on the back side will be you have your negative, I mean your electrons that can come in and interact with the backside of this molecule. So I'll try to show you some mechanism of that. But yeah, so this will be your anti-addition, and then as well as we will be adding an alcohol, which is OH. Okay, and so that's this here. OET, similar, right? And then you'll notice anti-addition as well. We have this wedge, and we have, or rather, dash, and then we have this wedge. Okay, whoops. Don't worry. Okay. So then we have what comes next. This is our merconium. So with this one, this is also, let me see. This is also Markovnikov. Okay. There is no rearrangements. Okay, no rearrangements, as well as no stereochemistry. Okay. Right. So no stereochemistry, as in it could be any combination, any which way, right? So that's why it's denoted kind of as this planar situation going on. Um, so this is happening. Let me just get another color. Um, so the same thing. So we're adding an H. So remember, we're adding this water molecule across the other molecule, right? So here's our H and our OH. So addition of water, right? And then whenever we see this BH3 THF, this will be your anti-Markovnikov. Um, You will get used to um recognizing these. At first, it's going to be very much like repetition, and you're going to have to try to do them over and over and over again, right? But you will get you, the more that you see it, the more that you do it. My biggest recommendation to you is just to keep doing the homework and keep doing the homework. And just getting that practice time in. That's the only way that honestly that you're gonna get better. So this is anti-Markovnikov, and it's also Sin edition. Okay, which means same side, right? So this has got no stereochemistry either. But yeah, so here's our water. Okay. Um, and then this one with our palladium, H2 with our palladium. This one's also Sin addition, and there's no rearrangement. Sin addition and no rear re whoops. That's so funny. Okay. Rearrangement. There we go. Perfect. So these ones will be same side. As you see here, we have the dash dash, or we have wedge wedge, right? And nothing's really changing. Um, your let me just go back through here. So all these carbons, I'm gonna just do them in the same color. These carbons are the same um when it comes to substituted. So those ones are the same. As you can see here, this is the more substituted carbon versus this is the less substituted carbon. But remember, we have this is an anti-Markovnikov, so that's why you're seeing OH, the remember bigger molecule being added to this red carbon atom. And then same thing. So this one as well. There's no difference. Oops, there's no difference in the carbon atoms here. Okay, so those are all the same too, and these green and reds are just arbitrary. The only time it matters is if there's green and red on one atom, like this. That's to denote a difference, but these and these are equivalent as far as meaning. Um, so anyway, so hopefully those are some good little tips. Um, Markovnikov has the more electronegative element adds to the most substituted carbon. So the more electronegative right here, O, adds to the most substituted carbon. And in this case, we don't really see, excuse me, any difference. So anyway, those are the old reactions, and then these are the newer ones. So you were asking how can we tell the difference? And I would say the biggest way to tell the difference of whether or not you're going to do a radical reaction is going to be if you see these or roar. Not to be mistaken with this reaction. Sorry about that. So this reaction, we do also have hydrogen peroxide, but a little bit different in that sense. So anyway, so when we have these radical substitutions or radical photo, light energy creating radicals in these reactions, you are going to see this in particular. And that's how you're going to know that you're going to be doing a radical versus something like this, where you're going to be having a reaction with a hydrogen. And so these ones, you're literally going to break the radicals, and you want to put the radical where the most substituted carbon would be, the most substituted atom. And just remember that we have these hydrogen all over. Okay. And so we make a decision on where the best, and there's two more here too, right? Where is the best place for this bromine to go? Okay. And so we want our radical to be the most stable. So this is the most stable carbon. So that will be where we will see the addition of bromine. Alrighty. Same thing with NBS is just another way of describing it. So NBS in short really just means that we have it's giving us an extremely low concentration of bromine, because otherwise if we have a high concentration of it, it will react with the carbon-carbon double bond. As we see up in here, right, in this example. It's just going to react with the carbon-carbon double bond instead of reacting with the hydrogen to create the radical substitution. So, or addition, excuse me. So that's why we see that. So when you see NBS, just know that you are adding a bromine to the most stable radical, and these will equally be the most stable radical positions because they are allylic. And remember that allylic has stability by resonance. So let's just pick one. Okay, let's say that we do this one, right? That's where our radical is going to be. So we'll put one here and one here, and we'll put one here, right? So what we end up, one as in one atom. So what we end up having is this resonance here, and that's why that would be the most stable carbon to put a radical on, and that's why we see this here. And not that you could tell the difference, but if I drew this like this, it would be the same thing, right? But really, if you just kind of turn this around and flip it, it is all literally the same thing. Excuse me. And anytime you see hydrogen peroxide, that is going to be anti-Markovnikov. Least substituted, most substituted, and we are just adding HBr across the bond, across the double bond. So there's your H, there's your Br. Right? Okay. So that's a quick review of the reactions. So I'm going to go through these problem sets that you had requested. So give the major and your question on this one. So when it comes to, I'm just going to go down your list. So when it comes to a HBr bond in an alkane reaction, the Br goes to a higher substituent compared to H. Yes. And so we see this well, we see this up here with this one. What we have is we would have, I'm just going to redraw it down here. Okay, so what we would have is we would have this carbon and we would have HBr. Okay, and so what you would end up having is what we're doing is we're breaking this pi bond here to free the electrons to interact. Okay, and then so what we would see is we would see these electrons coming in and interacting with the hydrogen, and this bromine coming in, or rather getting its own electron pair back, and then here are my electrons. So then this becomes, okay, so then this becomes this, and we're putting the hydrogen here on this carbon atom, right? We have to put it on one of these two carbon atoms, but because the blue carbon atom is the most substituted, that's where, and I'm going to draw this hydrogen atom on here, although you don't have to. It's perfectly legal not to. But we're going to have this carbocation on there because it is the most substituted. So you always want to put your carbocation on the most substituted. And if that's what it's talking about here with the rearrangements are possible, if you had, um, if you had, let's just say, right, let's just say that we had this rather, and then we reacted. What would happen is, it's incorrect, sorry, but it's kind of hard because, okay, anyway. So what would end up happening is we would have, oh, goodness, can't draw. There we go. What we would end up happening is we would put the H here, right? I know this is kind of crammed at the bottom here. And then we would have a cation here. And so, and remember that there's also an H here, okay? Just on this one, right? Not to be confused with this one up here. There's no H there because carbon has all of its, it satisfies its octet. So we have this H here. So what ends up happening, oopsies. So what ends up happening is we have what's known as a hydride shift. And what happens is this hydrogen comes over here and then we get, and we've had added that one there. Okay, so I'm not going to draw this hydrogen here anymore. But what we end up getting is now this hydrogen jumped, shifted, so to speak, over here, and then we have this here. So that's what you would see, and this would be an extra step in your mechanism. But that's not what we see up here in this orange one. So anyway, and then what we have is we have this Br that's floating around with it. And so then these would come in and attack this positive area. And that's what we would see. We would see this and the Br, right? And this is the same product. Okay, so that's what that one's about. For alkene reaction question 2, which is this one, can you explain a bit more of the mechanism behind the reaction? How do I know it does not do syn addition? Okay, so, and I kind of went over some of this. So what you're gonna have is when you have a molecule like this, what you're doing again is you're breaking the pi bond here. Remember, for every double bond, you have a sigma bond and then a pi bond. So what you're doing is you've got this big old atom here that wants to interact, right? And so what happens is you break this bond and you come in and you interact here. And what ends up happening is this, okay, what ends up happening is you have this carbocation here, right? And you have a Br negative floating around over here, right, from this original break. And then you've got this Br here. But because there's a positive charge and your bromine has lots of electrons, there's this little bit of wanting, whoops, wrong way. There's a little bit of this kind of wanting to interact, right? And so imagine that now these electrons from here, these two electrons here, are kind of wanting to like interact into this positive space a little bit. So it's kind of holding the space. Now, imagine that you're on a plane, like as in this is planar, right? So if this is planar, we've got this plane here, okay, and you've got this bromine up here, you know, on this side of the paper, so to speak, right? You've got this bromine up here on this side of the paper. Um, just imagine that this paper is actually this, hexose. Um, and so what you have then is this other bromine can come in, this other bromine can come in here from the bottom because we still have here, and I'm missing a methyl here. But because we still have this kind of positive charge going on, because bromine's not totally taking it over. There's actually, some resonance that's kind of going back and forth here. As you see, and then, if we kept going with this, right, then we would have this and we'd have, oops, not that one. Sorry. Let me put this here. So then we'd have this kind of here, and we'd have this bromine really kind of making a bond here, right? And so it's kind of like doing this little back and forth thing. Um, so anyway, so that's kind of what your like intermediates are for holding this space, right? And then once the bromine does come in and attack, what ends up happening is, because remember, bromine is a big molecule. It's very big. It takes up a lot of space, which means it has high electron density, um, big electron density cloud. So anyway, so we've got this here. How did I draw this before? We've got this here like this. And then so what ends up happening is because your bromines have to choose a side, we just put a wedge and we put a dash. And this is just to denote that our bromines are on opposite sides of each other. Oops, sorry. I'm not drawing it consistent with my other drawing here. Okay, sorry about that. Okay, so let me see where we're here. Oh, this cation. Okay, so, yes. So we'll draw this here with the bromine. Okay, and then that left this cation here, right? So then this one has to be on the back side, right? They have to be opposite. But what you'll notice is that, you can't have these three in the plane and only this one. So especially on a carbon, you only have four. And so that means that two are in the plane, one's coming out of the plane and one's going into the plane. So that would mean that this methyl has to be coming out of the plane as well, right? And we see that one, this one here, right here. Okay. Um, so yeah, so that is the mechanism on that. That's how we know it's not syn addition. A good way to kind of tell if your is what's your plane gonna be, right? Like what's your plane of existence going to be for this molecule. So we know that like a pentose is a planar molecule versus hexose is not, right? It takes up a lot of, it has more, as you saw, right? If we view it from the side, we kind of have this crown shape going on, right? So anyway, that's neither here nor there. So let's see. And then can you explain a little more? Okay. So as far as any tricks with heuristics, oh, I think I already mentioned this. Practice, 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 practice. You just have to keep seeing it and keep doing it and keep trying it. So let's see. Alkene reactions number 8. Can you explain how the mechanism was used to find the answer in this reaction? Yes. Okay. So this is going to be again one of those anti-addition, if we just scroll back up real quick, this is our anti-addition, um, reaction, right? And so, and just a little tip too, when you're doing these problems on the practice site, just um, have your reaction sheet, your summary reaction sheet up next to you. Practice it, obviously, but if you get stuck, just look at the sheet. It's not cheating, and it's going to help you to get better because you've never done this before, and so just trying to guess and sit there and be stumped on the paper is not going to help. What's going to help is doing the curved arrow pushing, making molecules, seeing if it works, counting your, am I, following the tech rule? Is my product matching up with my reactants, all that other stuff. So that's what's going to help you to learn this material, not trying to like memorize exactly what's happening and this and that and the other. It's like it literally comes down to practice. Um, so yeah, so number 8, which I believe is this one. So the what's going on here is we have um so it's much easier to see when you draw it out. Okay. And then so what we're doing is we're breaking this bond. We're breaking this pi bond and interacting here. And we're dumping those electrons onto the other bromine. Excuse me. And we want to put our cation because that's what we will end up creating. We want to put our cation on the most stable carbon of this. Okay. Um, and so that's what we will do. Um, or not cation, I'm sorry. This is not. Um, yeah, this is another one of those like bromine hanging on to both sides. So that's why it's like that. So here's this, and then here's our bromine, and then bromine. Okay, and then just for completeness, I'm gonna not a plus. I'm gonna put this bromine here just so you can see that it went there. Okay, plus this. Um, it's not a plus formal charge, but there's that bromine. So anyway, and then what ends up happening is we're kind of, holding on to this place here, right? Because it would be, right, a positive charge. It's not, but it's not a carbocation, but that's kind of like what it is. So we're kind of doing this like mini place holding with that. And then so what ends up happening is then we have ETOH, which again looks like this. And what's going to happen is this different color. This is going to have that backside attack on this. I remember we also have, we've got this hidden hydrogen here as well, right? So anyway, we're gonna have this backside attack that ends up taking place. And so what we have is we are here. O H A T. But we all know that um oxygen has absolutely no interest in being positive. Oxygen is an extremely greedy molecule and wants all of the um electrons to itself. So we won't see this last very long. So anyway, this oxygen is going to grab this hydrogen. These hydrogens are going to dump the electrons back on there. And so that's when we see Okay. Yeah, and there's our solution. I guess I just didn't do this. And then we're looking for chiral centers. So we know that this is going to be a chiral center because there are 4 different substituents on it. Um, this one This one is not a chiral center because it has 2 methyls. This is not a chiral center because they have 3 hydrogen. This is a chiral center, as we said. This is not a chiral center because it has 2 hydrogens. So yeah, so that's the only chiral center there that we see. What next? Okay, so can you explain how the mechanism was used to find the ring? Oh, which the so photobromation. What do they mean by resonance radical intermediate? Yeah. So what's happening here is we are looking for the most stable radical to anytime, remember, like I said before, anytime you see this HV, that means it's going to be a radical. And in the case of MBS, we are trying to add a BR. Okay, so I'm just going to put plus BR on here. Um, so what we need to do is we need to figure out where all our hydrogens are. And just for shorthand's sake, I'm just going to put blue lines for everywhere that there are hydrogen. But just know that like if I was doing this to completeness, this is how I would write it. Okay. So there's none on that one. There's 1 hydrogen here. There's 2 hydrogen here. There's 1 hydrogen here. And there are 3 on each of these. Okay. And then so if we remember our stability of radicals, um, a methyl group is the least stable, and then a first degree, second degree, third degree, and then I can't put it in here, but allylic benzylic, right? So allylic means that it is on a carbon that is next to a carbon double bond, or a double bond in some way. And so what that does is that creates resonance. And so which we worked on, I think last chapter, the chapter before. So this carbon is the only carbon that is right next to a benzene that uh yeah, it's the only carbon because this one over here doesn't have any hydrogen on it. So that's why it has to be this one. And then let's see. So if we draw this out, we have the H. Oh, whoops, not H. What am I doing? Okay. And if we want to do some curved arrow pushing, what we have is this and this. Imagine that there is a hydrogen there. And then we have this and this. What am I doing? Sorry. Um, okay. There. There we go. Okay. So, yeah. Your anyway, yes, your radical ends up over here. So, okay, this and this, right? And then let me do my hydrogen on here just so we can see it. Right? This and this. Okay, so our light energy, right? And then what we end up having is we have this double bond here, and then we have a radical here, and we have our Br radical here. This is times 2, right? And this radical is most stable because 1, 2, 3, 4, 5, 6. because what we end up having is we have this move here, this move here, and this move here, right? We can only move one at a time. And so what we end up having is we have this radical here and our double bond formed here. So we have stability by resonance. Because think of radicals as wild animals. If you put a wild animal in a small cage, it's not very happy. But if you put a wild animal in a big cage, it's pretty happy. So imagine that this space here is a much bigger cage, right? Than if we had this and it was stuck there, right? Because then realistically, its cage is only in this space, right? So more space that the radical has to move around, the more stable the radical is. So that's why the radical would be there, just to see it for, and then, yeah, I mean, what would happen is this would interact here, and this would interact here, and that would give us our final product. Right, that would give us a 1, 2, 3, 4, 5, 6, I think. That would give us our final product here. Okay. Um, and so that is our final product. I just didn't put my, but yeah, so that's our final product. And then so what they're saying is like, being able to do things by heuristics is like if you were to kind of cover this up and just look at this down here maybe and just say like, okay, I know that these are my allylic carbons, and so it has to be the carbons that are next to it. Well, the only positions that are in the allylic positions would be this carbon here and this carbon here. This carbon has 0 hydrogen, so it can't interact there, and this one has a hydrogen, so it can interact there. So that means through mechanism that my bromine must go on that carbon. Okay. Having a hard time figuring out the reagents. What would we just covered radical intermediate. I mean, kind of, right? Like this is both radical intermediate and radical resonance, or resonance radical intermediate. Yeah, those are kind of the same thing. So, I mean, they are the same thing, but I'm saying I think I covered this concept here. If you still have more questions about it, let me know. As far as reactions and reagents, you literally just have to practice these and see them over and over and over again. But this one, we know it would have to be either of these with light energy, because we're not starting off with any carbon-carbon double bonds or any double bonds, whatever, at all. There's no double bonds. And so that means that everything is kind of taken up, so to speak, right? So these are all, there's nowhere for this bromine to like necessarily interact with just like HBr or something, it's like, so, we need to like, this is a stable molecule, so, it's not really gonna interact, so we know that it has to be something with H nu, because we're gonna make a radical, we gotta somehow split up a bond to interact with to create that, so that's how you're gonna see that. Um, and we can tell that it was also on 3rd-degree radical, it says it down here. But we can tell that it was on the most stable area in which a radical or a cation could be. So that's why it would be either one of these solutions and not something that has maybe like peroxide or something in it. So give the provided, this is your question 2, having a hard time understanding how to find, what would be considered, okay, explain the radical reaction and reactions and how it differentiates. So I'm not sure what you mean by differentiates, but as far as like radical or cation intermediates and reactions, again, you're gonna see that up here at the top. And so anytime you see H nu, it's going to be a radical, right? And when we see roar like this, that also means that it's going to be a radical intermediate, um, and not a cation. So the good way to also recognize is that you have double bonds here that are breaking. So and then last but not least, the cumulative radical problems 8, the process of this type of problem. Okay, so given the provided BDEs, determine whether the following reaction will be exothermic, endothermic, and by how much. Give the reactions and enthalpy, change in H, etc., etc., etc. So you have to decide how many bonds are being broken and how many bonds are being made. So in this case, there are 2 bonds broken and 2 bonds made. So just look at your products and look at your reactants. So here's one, and here's 2 that are the most similar, right? And you can figure this out by either counting bonds, counting carbons, molecules, whatever it is, right? So in this case, we know that we are breaking and breaking, and over here we know that we are making and making. Okay, and so we can look at these BDEs and determine, so just by looking at this, two sigma bonds made broken, 2 sigma bonds made, that's not really like a telltale sign or anything. So we do have to do a little bit of math here. And so you would decide we have negative 46 and negative 98 and positive where is it? 88 and positive. Oh, whoops, this is 68. I'm like, what is going on? This is 68 and this is 88. Perfect. Um, so bonds that are broken release energy. I mean, your signs are arbitrary and it's going to be however it is that you understand it. So yeah, if you're taking energy out of the molecules, right? But you're adding the energy to the system. So it's like however it is that you want to think about it, right? So if you just decide that in this case, braking is, which is releasing energy, is negative, right? And making or putting in energy is positive. Just as long as you know what it is that you're doing. And then you'll literally just add all these things together. So we have negative 46 plus negative 98 plus 68 plus 88. And I get a total of 12 kcals per mole. And I decided that if the answer was positive, it means that I had to put in energy, which means it would be endothermic. Hopefully I'm getting the correct answer. Reaction enthalpy is negative exothermic. Yeah, see. Sorry about that. So the bonds are broken and these bonds are made. Yep. The sum of the energy cost, the sum of the energy of the bonds being broken is this, which we got, and the sum of the energy obtained or returned as a consequence of the reaction is this. Yep, this is put into the reaction. So you have, oh, I see what I did. Sorry. I just did it all at once. That was what I did. Okay, but anyway. So you would do 46 plus 98. I should have still worked out the same though. 46 plus 98, 144. And then returned, making new bonds than the energy required to break them. This is 146, and then 88 plus 68 is 156. So there we go, which equals -12. So I guess ignore what I said about it being arbitrary. It's my own interpretation of my own math. Right, so it costs more. So anyway, so more energy is returned by making the two bonds than the energy required to break it. So thus the reaction is exothermic. Yes. I'm gonna have to think on this one for a minute because it might be because it's midnight and I'm exhausted. I got 3 hours, so I apologize of sleep. But yes, I would have thought endothermic because but I guess you're getting the energy back. More energy is returned. Oh, the change is negative. Oh, I get it. Mm. Anyway, hopefully this can you explain the process for this type of problem? Okay, so let me see. And then classify the reaction and then substitution, right? So we're just rearrangement. No substitution, sorry, because we're just substituting here. We're just substituting them. Rearrangement is on the same molecule. So anyway, hopefully this was helpful. Let me know if you have any more questions. I'm happy to help. And I hope that you have some good luck with your exam.